You're welcome to my channel. Our topic for today is quadratic residues and reciprocity. Let's begin by way of introduction. A quadratic residue modulo n is a number that has a square root modulo n. Mathematically, A is a quadratic residue modulo n if there exists an integer x such that x squared will be congruent to A modulo n. If no such x exists, A is a quadratic non-residue modulo n. For example, let P be 11 equal to 11. Direct computation yields the table below. X modulo 11 means those numbers below 11. And they are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And x squared modulo 11 will give us 149533591. However, the quadratic residues that we have here are 1, 3, 4, 5, and 9. While the non-quadratic residues that we have from this table is 2, 6, 7, 8, and 10. Let's look at the legendary symbols. By definition, for P and odd prime, the legendary symbol A over P is equal to 0 if P divides A, and is 1 if A is a quadratic residue, and it is minus 1 if A is not a quadratic residue. Let's look at some examples. Is 2007 a quadratic residue modulo 29? Solution: 2007 over 29 will be equal to 6 over 29, will be equal to 2 over 29 times 3 over 29. Remember, 6 is an even number and they can be broken down into two prime numbers, 2 and 3. Now, 2 over 9 is a non-quadratic residue, and that is why we represent it as minus 1. Then 3 over 29 is also a non-quadratic residue, and we represent it as minus 1. So minus 1 times minus 1 is 1. Therefore, 2007 is a quadratic residue modulo 29. That is how to answer the question. Now let's look at quadratic reciprocity. This quadratic reciprocity was actually defined by Gauss. This is the fundamental relation between the legendary symbols P over Q and Q over P for distinct odd primes P and Q. He states that P over Q times Q over P is equal to minus 1 raised to power P minus 1 over 2 times Q minus 1 over 2. Now, what are the consequences of this expression? Number 1 is that if either P is congruent to 1 modulo 4 or Q is 1 modulo 4, then P over Q will be equal to Q over P. Another consequence of this quadratic reciprocity is if both P is being congruent to 3 modulo 4 and Q is congruent to 3 modulo 4, then P over Q will be equal to minus Q over P. This formula here is very, very important in trying to find quadratic residues through computation. So if you don't want to use the legendary symbol, you can actually use the Gauss quadratic reciprocity law, which is what we have just stated here. Now for the theorem, for any two distinct odd primes P and Q, P over Q times Q over P is equal to minus 1 raised to power P minus 1 times Q minus 1 divided by 4. So once you do this computation and you arrive at minus 1, then you should know that P is congruent to Q and they are congruent to 3 modulo 4. But if you arrive at plus 1, it means otherwise. How do we apply this Gauss law of quadratic reciprocity in solving problems? Now let's look at this example. Is 38 a quadratic residue modulo 43? Solution: 38 over 43 will give us 2 over 43 times 19 over 43. Since the numerator 38 is an even number, so you break it up into 2 primes, which is 2 and 19. And when you look at 2 over 43, the quadratic residue is minus 1. So that is how we got minus 19 over 43. And simplifying further, you are going to have 1. And you conclude, therefore, that since 38 is a quadratic residue modulo 9, since the evaluation gives us 1, then 38 is a quadratic residue modulo 9. That is the conclusion there. Let's look at another example. Should determine whether 357 is a quadratic residue modulo 661. Solution: we want to find 357 divided by 661. Although 661 is prime, but 357 is not. So we cannot apply quadratic reciprocity directly. Therefore, you have to factor the numerator. And when you factor the numerator, you're going to have that 357 over 661 will be equal to 3 over 661 times 7 over 661 times 17 over 661. That's breaking it up into primes. And when you continue to evaluate further, you're going to discover that 3 over 661 will give us plus 1. 7 over 661 will give us minus 1, because that one is non-quadratic residue. Then 17 over 661 will give us plus 1, because 17 over 661 is a quadratic residue. So when you now take the product of plus 1, minus 1, and 1, you're going to have minus 1. So therefore, you conclude that 357 is not a quadratic residue modulo 661. So that is how this is done. Now let's look at the Euler's criterion. By definition, if P is an odd prime, then for any residue class A, it is true that A over P is congruent to A raised to power P minus 1 over 2 modulo P. That is a formula. So with this formula, we can easily apply the Euler's criterion to determine whether a modulo n is quadratic residue or not. Now, let's verify quadratic reciprocity for when P is 17 and Q is 19. Solution: using Euler's criterion, we evaluate that 17 over 19 will give us 17 being congruent to C squared modulo 19. Then 19 over 17 will give us 1 modulo 17. And you now evaluate the both by multiplication. So 17 over 19 times 19 over 17 will give us 1, as claimed. Let's look at another example here. We should verify quadratic reciprocity for when P is 23 and Q is 43. Using the Euler's criterion, this is direct. You simply apply the formula, and whatever the evaluation you get tells you what the answer is. So for 23 over 43, when you apply the Euler's criterion, you will simply have 1 modulo 43. Now for 43 over 23, when you also apply the Euler's criterion, you're going to have minus 1 modulo 23. Indeed, 43 is a square modulo 23. One can verify by writing down all the quadratic residues modulo 23. Okay, this agrees with quadratic reciprocity since both 23 and 43 are congruent to 3 modulo 4, and their product will give us minus 1, as claimed. Let's look at this example. And our final example in quadratic residues and quadratic reciprocity, we should evaluate minus 72 over 131. Now, minus 72 over 131, as usual, the numerator 72 is an even number. So you have to break it up into 2 primes, which we have done. And it gives us minus 1 over 131 times 6 squared over 161 times 2 over 131. And when you apply the Euler criterion here, you're going to have minus 2 over 131. Now, continuing further, we try to expand 2 over 131 to see what is going to give to us. Then at the end, we have 1 modulo 131, telling us that it's a quadratic residue. Now, there is this subtopic here, arithmetic function. Is actually different from quadratic residues and reciprocity. What is an arithmetic function? If the prime factorization of n greater than 1 is p1 alpha 1, p2 alpha 2, p3 alpha 3, and so on, up to pk alpha k, then the number of positive divisors of this number is tau n, or is represented as tau n, number of positive divisors. While sum of positive divisors is represented as sigma n, and the formulas are represented in the definition. Let's look at some examples on how to apply tau n and sigma n. Find the number of distinct positive integral divisors and their sum for the integer 56,700. Solution. Expressing in prime factorization canonical form, we have 56,700 can be expressed as 2 raised to power 2 times 3 raised to power 4 times 5 raised to power 2 times 7 raised to power 1. Now, since you have known that, you can recall the arithmetic function tau n, where our n is 56,700. Then, when you substitute properly into the expression there, you're going to have 90 for tau n. While for sigma n, where n is also 56,700, when you substitute properly, you're also going to have 210,056. So we've been able to compute our tau n and sigma n. Thank you very much.